All right, next we're going to look at uniform circular motion, and kind of a guiding question to consider here is what causes something to move in a circle? And so we want to start off by making sure we're on the same page with our definition. So uniform circular motion occurs when an object moves along a circular, surprise I know, path with a constant velocity. I should say constant angular velocity, or let's change this to a better word, speed. It's a bit sloppy of me, because again, if we're changing our direction, that's going to change the velocity. But in this case, we're talking about speed more specifically. So uniform circular motion occurs when an object moves along a circular path with a constant speed. And we can look at linear or angular speed more or less, because if it's going to be a circular path, then the only way you can keep it circular and have a constant linear speed is by also having a constant angular speed, and vice versa. So to maintain that uniform circular motion, an object must only turn and not speed up or slow down. So in other words, it will accelerate because it's turning, but it's not going to cause, that acceleration isn't a speeding up or slowing down, it's just a turning. In other words, the linear acceleration must always be pointed towards the center of the path. So it's always turning towards the center, hence the reason that it ends up going in a circle, right? If you can imagine always turning towards the center, you're going to keep going in a circle. And if your center-pointed acceleration is always perpendicular to your velocity, that means it's always just turning it and never speeding it up or slowing it down. So that center-pointed acceleration is called centripetal acceleration. So centripetal acceleration is an acceleration pointed towards the center of a circular path. And so we know that accelerations just don't happen randomly. They must be caused by a non-zero net force. This is Newton's second law. So we have an acceleration that's always pointed towards the center of a circular path. We call that centripetal. The kind of root of this is roughly, don't quote me on this, but it's roughly center seeking, so pointed towards the center. So if we have this acceleration constantly pointed towards the center, and we know that there has to be some sort of non-zero net force to cause that acceleration, then we call this net force a centripetal force. So this is a force that's pointed towards the center to cause the centripetal acceleration. So a centripetal force is a net force that's pointed towards the center of a circular path. Now, what's important to note about this is it's not a different kind of force. It's not the same kind of idea as like a frictional force or a tension force or a thrust force. Instead, we can think of it more like a descriptor of a force. So if a gravitational force can be a centripetal force. A normal force can be a centripetal force. A friction force can also be a centripetal force. They can all be centripetal forces. And so we have these examples here. For example, a toy tied to a string that's then spun around. That's got a tension as the centripetal force. The tension is what's keeping that toy moving in a circle. It's always pulling towards the hand that's spinning it. With a satellite orbiting the Earth, well, we have gravity always pulling us towards the center, right? So we have in this case gravity serving as a centripetal force. Now, we could also have some interesting situations where maybe you've got, something that's spinning, and it might have a normal force and a frictional force pushing on it. If it's got both of those, then the net force of normal plus frictional would be what we call our centripetal force in that case. So it doesn't have to be, it's not like its own kind of force, it's more of a description of a singular force or a net force. All right, so key equations and relationships. The centripetal acceleration is going to be equal to v squared over r, which is also equal to r omega squared. So this is if you're talking about linear quantities. This is if you're talking about angular quantities. So if you know how quickly how fast the speed is, you can use this left side, v squared, square the speed, divide it by the radius. If you know how kind of fast the rotation is, you know it's doing 2 rotations a second, you can find the angular speed, square it, and multiply by r. And this is just from knowing that v equals r omega. Sorry, I don't know why I put that square there. So if v equals r omega, then when you plug in v or r omega into the top of this expression here, you're going to get r omega squared as a result. Centripetal force is just the mass times the centripetal acceleration, because this is just Newton's second law. Now notice we don't have a net force here. That's because centripetal force could be a net force. It also could be kind of pretend treated as a singular force. But in other words, that also equals mv squared over r, or mr omega squared. And so all of these are kind of just different ways of looking at it. As we go on and practice with things, you'll see how these equations get used in context. If you have any questions, let me know, but otherwise, I'll see you in the next video.